So this is a stimulated emission rate in continuity to the previous video. The Einstein's stimulated emission rate, that is a B21, and now sometimes I'm using the letter A and sometimes using as letter B. If you make a small review of my previous video, for a stimulated absorption also, I have used the letter A1, B12. So for stimulated, I have used the letter B. If you look at stimulated, letter B, and for spontaneous, I am using the letter A. That is the clarification you have to get into the mind. For stimulated absorption or stimulated emission, I am using the letter B. And where you know the suffix 1 to represents energy state 1 to energy state 2 and energy state 2 to 1. And for spontaneous, I am using the letter A. So now we have total equations 3. Equation 1 is for stimulated absorption. Equation 2 is for spontaneous emission. Equation 3 is for a stimulated emission rate. With these 3 equations, we will put forward our derivation. How the derivation proceeds, right? So this derivation is a totally a simple mathematical calculation where you will be feeling very comfortable, where there will not be any huge steps or just a recall of some of the important parameters where we have learned almost in a quantum mechanics. So we'll just try to recall some equations right there. So let me give a review of a small for a small span for the Einstein equations. We started with saying that let N1 be the number of atoms in a ground energy level, that is a E1 level, and N2 is the number of atoms in E2 level, and rho nu represents the density of photons, right? Now, and first what we have discussed is stimulated absorption, and I started with the diagram saying like this. So where this is E1 and say this is E2, N1, N2, and all these are atoms, and now there is a stimulating photon, rho nu, and Einstein's that is absorption rate mathematical depends on N1 and proportional to rho nu, and the equality, that is stimulated absorption rate is equal to, so B12 N1 rho nu. I called this as equation 1, and after that then we have gone to a spontaneous emission. So where the ground level atoms will be excited to higher energy atom, I will call it as exciting. And here spontaneous, for spontaneous emission, where we have gone for the diagram like E1 and E2, where they will be residing up to the span of 10 power minus 8 seconds, and there will be de-exciting. De-exciting is the process of getting down or to the ground energy level by emitting photons. So this is not the process required for the laser action. And now for the spontaneous emission rate, I am writing in a shortcut manner in order to save the time. So this depends upon N2, that is proportionality constant. If I write a spontaneous emission rate is equal to proportionality, I am removing, and where I am calling it as A21 from second state to first state, and where this is N2, and I am calling it as equation 3. And the third step is stimulated emission. And for the stimulated emission, so this is the diagram, and there will be large number of atoms in the higher energy level E2, and lower energy level E1. Now I'll use a stimulating photon 1 rho nu, and this will be and as a result this atom will be de-excited, and you will be getting a photon 2, and these two photons interact with another 2 atoms and giving rise to 4 photons, and these 4 photons interacts with another 4 atoms and you will be getting another 8 photons like this, and as a result the light will be amplified by a process called as stimulated emission. Therefore, hence the name a laser. So Einstein said that what are the important dependencies or depending parameters for the stimulated emission to occur very effectively, that is called as rate, depends on, for this the number must be very high in higher energy level, okay, that is N2, and there must be large number of photons also, therefore rho nu. So clubbing these two, therefore a stimulated emission rate proportional to N2 rho nu. If I remove the proportionality, so stimulated emission rate is equal to B 21, so rho nu into N2. So I am calling it as equation 3. So these are the 3 equations where we have discussed in the previous session. That is, equation 1 is for stimulated absorption rate. This is Einstein's stimulated absorption rate. You just add a word to this constant by writing this B12 represents Einstein's stimulated absorption rate, and equation, this is equation 2. Simple correction, right? And this is a spontaneous emission rate, where A21 is Einstein's spontaneous emission rate, and this is equation 3, where B12 is Einstein's stimulated emission rate. So these are the 3 parameters, that is equation 1, equation 2, and equation 3. With these 3 equations, we'll just get into it. Now, if you look very closely, I make the 3 process into 2 classes, that is upward transition and downward transition. If you look at stimulated absorption, this is an upward transition, means the atoms will be moving upward. If you look at the spontaneous emission, this is a downward transition. This stimulated absorption emission is also a downward transition. Now I will make a relation. I will try to connect equation 1, equation 2 and equation 3 with a mathematical notation. Right? How I will connect these 3 equations mathematically? Yet, if you closely observe, this is a small assumption or small technique used by the physicist. Therefore, upward transition of atoms means the atoms moving upward will definitely at some time or another will be equal to downward transitions of atoms, right? This is an important parameter. The atoms which has jumped to the higher energy level at some time or another, or either with a lifetime or mean lifetime or sometime, they definitely must get down. Therefore, upward transitions is equal to downward transition. And Einstein intelligently observed that the upward transition is by looking at the 3 equations 1, 2 and 3 what I have written, a stimulated absorption rate is equal to, what are the downward transitions? Downward transitions are spontaneous emission rate plus there is another downward transition also, that is a stimulated emission rate. Therefore, stimulated absorption rate, that is equation 1, he is using the equation 1 is equal to equation 2 and also equation to the 3, that is equation 1, equation 2 and then plus equation 3, right? So then what is this equation 1? So you just scroll my video, so a little the previous video a little back side, and if you look at the stimulated absorption rate will be like that is so B12 from ground level to, so rho nu, so N1 is equal to, so spontaneous A21, so N2 plus here B21 rho nu and N2. If this this equation is done by you. If we are able to write this equation, the three parameters, by connecting with a beautiful principle proposed by the Einstein, that upward transition, that is the atoms which has raised to the higher energy level, at some time or another they get down back. With this relation, he connected the three equations like this. Then your interesting subject mathematics starts, where we keep all the terms in a parameter. Therefore, B12 rho nu n1. I will try to bring that parameter, that is that content into, and that is A21. So B12 rho nu n1 minus B21 rho nu n2 is equal to A21 n2 plus A21 n2 plus B21 rho nu into n2. Right? No, this is enough. This one, that is a A21. And here we have brought that is a B21 rho nu into this side. Then now I will take a rho nu rho nu as a common term, and therefore B12 n1 minus B21 n2 is equal to A21 n2. And then rho nu is equal to, I'll send this parameter into the A21 n2 by B12 n1 minus B21 n2. And this is what I had done. So that is, I had taken this term into the denominator. And once again, therefore, rho nu is equal to, now I will take n2 B21 as a common. I will take B21 n2 from as a common term and divide the numerator and the denominator. So what happens? A21 by, because n2 will be get cancelled, right? So no problem, I will try to write an extra step, right? So right, then B21 n2 as a common term. So what happens here? B12 n1 by B21 n2 minus 1. Here, this I had taken out the common term. Then I will try to separate it out. Therefore, rho nu is equal to A21 n2 by B21 n2. So, and B12 n1 by B21 n2 minus 1. Now in the numerator part, here I have taken separated, and as a result here n2 will get cancelled, and as a result, therefore rho nu is equal to A21 by B21 by B12 n1 by B21 n2 minus 1. Right? So this is a part here, right? Let me bifurcate the board. Right. So now here, what I'll do is, here we have to know the terms of n1 and n2. Right? Come back. N1 is the number of atoms in the ground level, and n2 is the number of atoms in the higher energy level. If we know the value of n1 and n2, we can simplify this equation a little bit. So for that, the Boltzmann distribution law, this topic was already discussed. So if you look at the quantum mechanics chapter unit 1, we already discussed the Boltzmann distribution of atoms. The Boltzmann distribution of atoms in various energy levels. Various energy levels distribution is given by Ni is equal to, so N naught exponential minus Ei by kT. This is the distribution of the atoms in various energy levels. You just refer the quantum mechanics, and if I refer the diagram, you will just get recognized, so that the number of atoms will be large in ground energy level, and as the energy level increases, the atoms number will be gradually decreasing. This is an exponential decrease of the atoms. So please refer the quantum mechanics unit 1. This is exponentially decreasing as the energy is increasing. This is a E1 level, this is a E2 level, this is E3 level, and this is E4 level. As energy is increasing, so the number of atoms will be gradually increasing, or the number of atoms will be gradually decreasing, that is exponentially decreasing. So where I is equal to number of states, or where if I take I is equal to 1. Therefore, if I take I is equal to 1, if I is equal to 1, 2, 3, 4, so on, if I is equal to 1, therefore N1 is equal to N0 exponential minus E1 by KT. Right? Similarly, N2 is equal to N0 exponential. Similarly, N2 is equal to N0 exponential minus E2 by KT. Now I had calculated N1 and N2 values. N1 is the number of atoms in the ground energy level. N2 is the number of atoms in this higher energy level. I had calculated N1 and N2 with the help of Boltzmann distribution law. Then, therefore, N1 by N2, simply if I take N1 by N2 ratio, N0 will be cancelled, and exponential, here you be a little cautious, exponential will be common, and by exponential. So I will take the denominator exponential into the numerator, and as a result this will be in the denominator. When I bring into the numerator, this becomes positive. Therefore, E2 minus E1 by KT. Alright. Then what is this E1 minus E2? So let me draw a diagram. E2 is the highest energy level, and E1 is the lowest energy level. The difference of this one, that is higher energy level to lower energy level, will be emitted as a photon. So therefore, this the difference of these E2 minus E1 is emitted as a photon. Therefore, N1 by N2 is equal to exponential of E2 minus E1. E2 minus E1 is nothing but h nu by KT. So now I will substitute the N1 by N2 value in this expression. Right. So coming to the continuation of our derivation. So which is a simple part, and therefore rho nu is equal to A21 by B21 by, so B12 by B21 by B21, N1 by N2 is nothing but so exponential h nu by KT minus 1, right? So this is the expression for the density of photons. Now I will try to give an expression to the number. This I will call it as equation 4. The above equation 4 is similar to, is same as the density of photons rho nu in Planck's radiation law. What is the Planck's radiation law? Planck's radiation law is the distribution of photons in various energy levels, and this we had discussed in our unit 1, and our unit 1 name is quantum mechanics. You just refer unit 1, and the topic is the last topic, so you just try to refer your notebooks, and we had discussed the derivation right now. So, and as a result, so and you refer the quantum mechanics, and according to quantum mechanics, the Planck's radiation law is Planck's radiation law is rho nu in terms of frequencies 8 pi h nu cube by c cube, 8 pi h nu cube by c cube into 1 by exponential h nu by kt minus 1. So this is the Planck's radiation law. Now you call this as equation 5. Now if you compare equation 4 and 5, comparing equation 4 and 5, if you look at the terms are similar terms. On the LHS side the terms are similar. So on comparing, so what happens here? This exponent term and this exponent term is same. Before the exponent term there is a b12 by b21, but here before the exponent term there is nothing here. There is nothing here means here the value is 1. So and here a21 by b21 is approximately equal to the constant here. On comparing, a21 by b21 is equal to 8 pi h nu cube by c cube. This expression is in terms of frequencies. So we have derived in the quantum mechanics where we have derived the expression in terms of wavelength also. That is wavelength also 8 pi h lambda, 8 pi hc by lambda power 5, 1 by exponential hc by lambda kt. That converted into frequency terms. So therefore on comparing, this term a21 by b21 will be approximately equal to 8 pi h nu by c cube, and this term and this term, the bracket terms are compared, and before the exponent term there is nothing here. There is nothing here means 1. Therefore b12 by b21 is equal to 1. So these are the two expressions. This is expression 1 and say this is expression 2. The expression 1 and expression 2 are Einstein coefficients, where this a21, A is a spontaneous emission, B is stimulated emission, and this is also here. If you look from this B12 is equal to B21, because B is for stimulated, B is also for stimulated, hence we can tally that these both are equal. So this is the Einstein coefficient. So you call this as equation some x and you call this equation y. Then the equations x and y are Einstein coefficients. Right? So this is the derivation for the Einstein coefficients. Right? So this is an important essay question which appears 85% of the probability in your examination. Right? So let me give a clarification for the overall review for the Einstein coefficients. How we have defined Einstein coefficients? Overall view, I will write. What is Einstein coefficients? Derivation for Einstein coefficients. So first we had defined what are Einstein coefficients. You just refer. Review my video, Einstein coefficients definition, and started with stimulated absorption rate calculated, that we call it as equation 1, and then we had calculated spontaneous emission rate and we call it as equation 2. Then we had calculated stimulated emission rate, then we had called it equation 3. Then an important principle called as upward transition is equal to downward transition. Therefore equation 1 is becoming equal to equation 2 and 3, and I had calculated rho nu is equal to we got an expression, and in the expression we had calculated n1 by n2 value, and in the n1 by n2 value we had come across exponential of e2 minus e1 by kt, and I had called that we had calculated e2 minus e1 as a h nu and substituted n1 by n2 in a rho nu, and we had got an expression for a rho nu as a a21 by, so a21 by b21 by something b12 into something into exponential of something, and then we had compared this equation compared this equation with the Planck's radiation law, and after the Planck's radiation law comparison, we had got A21 by B21 as 8 pi h nu by c cube, and B12 by B21 as 1, and from this equation we had make an equality relation where this equation x and equation y are the Einstein coefficients. So this is an important derivation. Then in the next session we'll be discussing the characteristics of laser, right?